Hello, we are Team Fission Chips, and our project is focused on the prototyping of a sample folding mechanism subsystem for the Radionuclide Aerosol Sampler Analyzer, or RASA 2.0.
In 1986, an explosion and fire at the Chernobyl power plant resulted in the catastrophic release of radioactive material throughout Europe and the rest of the world. In the aftermath of the disaster, the global community became painfully aware of the need for large-scale atmospheric radiation monitoring.
To address this concern, Pacific Northwest National Lab created the Radionuclide Aerosol Sampler Analyzer, or RASA for short. The RASA 1.0 was developed and deployed into a global network soon after and has been used ever since, even being the first to detect the radiation from the 2011 Fukushima disaster.
Now, the original RASA system is being updated. RASA 2.0 features a myriad of improvements over the original. One important distinction between RASA 1.0 and RASA 2.0 is sample delivery. RASA 1.0 used a continuous feed system, but the updated RASA 2.0 system separates samples into discrete parts.
This is where Fission Chips comes in. Our team has been tasked with developing a new method for folding and storing 32 layers of mylar, which serve as the container and transportation vehicle for the precipitated radionuclide aerosol samples. Our team aims to develop a method of folding that reliably and repeatedly folds the mylar web into discrete samples with negligible loss, advanced on a continuous linear feed system.
The largest challenge we face is accounting for tricky mylar properties when trying to advance the system, heat seal layers, or place tension on the feed. In order to meet the challenges, we have identified 4 subsystems: the tensioner, heat seal encapsulator, the jelly roller, and the packager.
As the mylar exits the sample collector, the 32 sheets are layered between an additional wider top and bottom sheet that are heat sealed together using a rolling heat sealer. The purpose of heat sealing is to encapsulate the sample. These 2 larger sheets are not used in the sample collecting themselves and can therefore be manipulated by other subsystems without the risk of dirtying the sample.
The tensioner keeps the layered mylar sheets under 3 to 5 pounds of tension throughout the process. This ensures the material can be manipulated without the layers separating or sliding past each other.
Finally, the packager closes the rolled material between 2 clips so that the mylar keeps the rolled up shape when the insert is removed.
The jelly roller subsystem wraps the encapsulated mylar into an appropriately sized package that can be placed into the detector using a rotating fork insert. The primary function requires 3 different motion systems: one to translate the insert along the length of the sample, one to rotate the insert, and one to translate the width of the sample so that the insert can be retreated from the folded sample.
The 4-step process can be seen here. From the starting state, the insert translates into the sample area. Next, the insert simultaneously translates and rotates to produce the rolled sample. The packager clip is then inserted. Once the sample is held together with the clip, the insert retreats from the sample and it translates back to the beginning state of the subsystem. This overall CAD rendering shows the flow of the 4 subfunctions. The mylar enters the heat sealing encapsulator and then moves to the jelly roller and packager. The tensioner is not shown, but is used before the heat sealing encapsulator to ensure that the entire system stays in tension.
A functional prototype of the jelly roller was produced as our client, PNNL, was primarily concerned with manipulation of the sample into a smaller size suitable for the detector. We further provide a proof of concept for the other 3 subsystems, as identifying additional necessary subsystems was a secondary concern that PNNL personnel worked with us on to address.
Looking forward, PNNL plans to take the issues, solutions, and ideas we have identified in this project to combine the 4 subsystems and incorporate them into a functioning RASA 2.0. Fission Chips would also like to extend a special thanks to our clients, Dr. Harry Miley and Dr. Lance Leidy at PNNL, and Dr. Michael Swanwick at Creary, as well as our faculty advisor at Georgia Tech, Dr. Sprickle.